We'll assume you know how iodine and red phosphorus together can reduce secondary alcohols to alkanes. We've done it before in a previous video using a slight variation on this using hypophosphorus acid, and it worked well. We got a viewer question which was whether or not aluminium would substitute in place of phosphorus. After all, it does seem to work to some extent for making alkyl iodides. Initially we thought no way. But then we researched some more about the iodine and red phosphorus reduction mechanism and we figured that we'd give it a go. We'll explain a bit more about the theory later. So let's go through the reagents. First we've got aluminium foil, and we've weighed out 1.4 grams of it. This is going to be a fairly large excess to what we need in theory to react with all the iodine. And next we've got our iodine. We're using 4.9 grams of iodine powder here. Note that this is recovered from another reaction, so it's pure but might be very slightly damp. And here's our reduction substrate. As in the previous reaction we're going to use mandelic acid. Firstly because we've proved it works in a previous reaction. Secondly because the product of reduction is phenylacetic acid, and this should be very apparent by its sickly honey-like aroma. And here's 2 grams of mandelic acid. We prepared this in a previous video, so check that out for details if you want to know how to make this. Okay, here's the lineup. Before we did the reaction we just wanted to test and see how aluminium and iodine reacted together in elemental form, just to check it wasn't going to be dangerous. So here's some iodine on some aluminium foil. And to spice it up, here's some aluminium metal powder as well. Let's wait and see if anything happens. And the answer was very little. We could feel the bottom of the sheet warming up, so there's an exothermic reaction, but it's not violent, at least at low temperatures. So we figured that with a solvent we should be okay. So let's get set up. We're going to use a 250 ml flask on the heating mantle and equipped with magnetic stirring for the reaction. That gives us lots of space in case anything exciting does happen. We've got a little reflux condenser attached to the top. Let's get this started. Okay, we did some research on solvents, and we found that the iodine and red phosphorus reaction has been done very effectively using acetic or propionic acid. Aluminium isn't particularly reactive towards these acids, so we'll try this out. Let's just dismantle the condenser for a moment. And here's 25 ml of pure anhydrous propionic acid. That should dissolve our iodine and substrate effectively as well. Okay, now we're rocking. Let's start off with the iodine and get this into the reaction flask. It dissolves in the propionic acid rapidly, forming a brown-colored solution. Okay, all in now. So next for our substrate, the mandelic acid. This also seems to dissolve well. We'll start by adding about 1/3 of the aluminium foil. And now we're going to leave this stirring at room temperature, just to see what happens and if any spontaneous reactions starts. This is going to be boring to start with, so in the meantime we'll talk a little bit about the theory here and why we figured that actually this isn't totally a crazy idea. Here's the iodine and red phosphorus reaction. Very simply, the phosphorus and iodine react forming Pi3. This first of all reacts with the alcohol to iodinate it, forming an intermediate compound. The hydroxyl from the alcohol ends up irreversibly tied to the phosphorus and eventually forms phosphorus acid. But in a second step, a reduction can occur. In the presence of hydrogen iodide, the intermediate can be reduced, forming an alkane, in our case, phenylacetic acid. The result of this reaction is iodine, which then reacts with more red phosphorus to form Pi3 again. So here's a simplified overall schema. This works because the phosphorus can react with iodine, the Pi3 can react with the alcohol, and with a tiny bit of water present, high will be generated, which acts as the reducing agent, and keeps the cycle going. What we figured was that we now know that aluminium does work together with iodine and can react with simple alcohols such as ethanol to form ethyl iodide. We've tested this in a previous video. We also know that aluminium iodide is highly reactive with water and will generate hydrogen iodide. And the aluminium hydroxide formed is highly stable. Like the phosphorus acid, it's not going to participate any further. So we've in theory potentially got everything we need in one place to perform the same reduction, only using aluminium in place of red phosphorus. Of course, theory is one thing. Well, at room temperature after 15 minutes there's no visible reaction, so we're going to start to gently warm the mixture now. And some smoke-like fumes are starting to appear in the flask. A few more minutes of heating and the color seems to be changing as well. And soon we notice white needle-like crystals forming on the inside of the flask. Definitely a reaction occurring. At this point we add the rest of the aluminium foil. And we slowly raise the temperature until the mixture starts to reflux. And pretty soon the color of the iodine starts to fade to a paler yellow. The mixture is becoming slightly frothy. After a while the frothiness died down. We're probably about 50 minutes into the reaction now. To give this the best chance of reacting, we then allowed the mixture to stir and reflux for another 2 hours. Here we go. We then allowed to cool back down to room temperature again slowly. We transferred into a beaker, and in order to quench any remaining aluminium iodide we added a couple of ice cubes. No real obvious reaction at this point. Well, pretty much everything apart from phenylacetic acid should be water soluble. So we're going to start by adding 80 ml of cold water to the reaction mixture. Yum yum, looks like coffee with luxury aluminium flakes. Most of the iodine color is gone, which is encouraging. If the aluminium had simply reacted with the propionic acid, then we would guess that there would still be a huge amount of iodine. There's also an insoluble scum of something floating on the surface. Let's start by adding a little bit of sodium hydrogen sulfite, which should reduce any residual iodine, and make this a bit easier to work with. We then added a small amount of 50% sulfuric acid to see if this would dissolve the gray cloudiness in the mixture. It did, but not much, so we covered the beaker and left it in the fridge for a few hours to chill down and for the precipitate to settle. Here's the result a few hours later. There's a gray solid on the bottom of the beaker which we are assuming is unreacted aluminium. We're going to decant as much of the clear liquid we can into a separating funnel now. The solids might contain some organic products, but if there's any phenylacetic acid in here we should also be able to get some out of the liquid as well. We were fairly cautious not to get any solids into the funnel, as you can see. So let's see how this goes. We'll first try to extract the aqueous mixture using dichloromethane. So here's 25 ml. Let's give this a really good shake for a few minutes. And now we'll allow to separate. One issue we're going to have is that the DCM will also dissolve out some of the propionic acid as well, but let's see what we get. The aroma of phenylacetic acid is very strong and potent and should be easily recognizable above even the sickly propionic aroma. Looking good. So let's now drain off our bottom DCM layer. And now we'll place this in a petri dish and evaporate the DCM off in a warm place to see what we've got. And here we are. A fair bit of liquid remaining, and we can tell immediately from the aroma that unfortunately it's pretty much propionic acid. This reaction hasn't generated any phenylacetic acid in a significant amount. This isn't too surprising, and is basically what we were expecting. But there is a surprise on going back to the aqueous layer now that a chunk of the propionic acid has been extracted out. It's not strong, and definitely faint, but it's unmistakable. There's a rubbery petrochemically sickly honey acacia aroma in there in the background. Call us crazy if you will, but it's there. We did another extraction of the mixture in the beaker using diethyl ether. Again, this seemed to only give us a small amount of propionic acid. So it's clear, this reaction as it stands doesn't reduce mandelic acid. But we can't help but feel a sense of unfinished business here. Perhaps our choice of solvent was totally wrong and the acid just dissolved the metal. Perhaps you need a little bit more water, or perhaps anhydrous conditions. Maybe you need a catalytic amount of hydroiodic acid in there as well to start with to get things moving. This might all be bullshit, and there's really no chance, but the background aroma is there and it tells us that maybe, just maybe with the right conditions, this can yield something. It's a cliffhanger, and unfortunately we don't have time to play with it any further. Perhaps someone else out there would like to take on the challenge? This is our last reaction video, but we've got a few more interesting things to show you, so there will be a few more videos coming up. Thanks for watching and stay tuned.